Before I begin this presentation, I would like to ask you to keep this idea of equilibrium in the back of your head. This presentation is going to be lengthy, and at some points I will have to attribute some phenomena to chemical favorability. This is the universe's way of maintaining stability. With that said, let's get started. Matter is defined as anything that occupies space and has mass. On Earth, it comes in three familiar forms: solids, liquids, and gases. All matter is composed of chemical elements, which are substances that cannot be broken down by ordinary chemical means. Today, chemists recognize 92 naturally occurring elements and a few dozen synthetic ones. In this image, we see two elements, chlorine, a gas, and sodium, a metal. Notice how the elements have been abbreviated Na and Cl. Every element has a symbol which comes from the first few letters of its English, Latin, or German name. For example, Na comes from the Latin word natrium. A compound is a combination of two or more elements. In this example, sodium and chlorine bonded together in a 1-to-1 ratio form table salt. Salt also serves as a prime example of how compounds often have completely different properties from the elements that compose them. These can be thought of as emergent properties. About 25 elements are important to life. As you can see in the table, 4 of these make up about 96% of the weight of the human body and serve as key ingredients in biological molecules. Trace elements, which aren't listed here, are important in very minute quantities and are often added to food we eat. For example, fluoride is added to dental products and water. It helps our teeth become strong and healthy by reinforcing the enamel. Another example includes iodized salt. Iodine is a very important part of thyroxine, which is a hormone secreted by the thyroid gland. It helps us control our metabolism, so when it is lacking in our diet, the gland may enlarge in a condition known as goiter. Okay, I want you to imagine a block of 100% pure carbon. Now think of chipping away at that block, piece by piece. Although this scenario is fairly unrealistic, what we'd expect to happen is that at some point we'd be left with a particle so small that it simply couldn't be cut. Chemists call this particle an atom. The word atom comes from the Greek word atomos, meaning indivisible, and it was rightfully named that way because it is the smallest unit of matter that still retains the properties of an element. Physicists have recognized hundreds of subatomic particles that make up the atom, but only 3 of them are actually relevant to us. They are the proton, neutron, and electron. Admittingly, conceptualizing something so small is very difficult, so you'll have to bear with me for the next minute. An atom is composed of electrons and a nucleus. The nucleus is made out of neutrons and protons, tightly packed together. Since the positively charged protons repel each other, neutrons, which contribute to the nuclear strong force without adding any additional repulsion, act as a sort of atomic glue, binding the nucleus together. In contrast, the electron is a negatively charged particle, swirling around at almost the speed of light. As you can probably imagine, by moving so fast, the electron is for all practical reasons everywhere at once. In fact, the only thing keeping it near the nucleus is the electromagnetic force exerted by protons in the nucleus. For this reason, we tend to describe this by using the analogy of a cloud that represents where the electron is around 90% of the time. Although this cloud model is technically more accurate, it is not very visually appealing, so for the remainder of this video, we'll use a more planet and orbit diagram. Now, I just want to clarify that these images are not in any way to scale of what an atom actually looks like. A more accurate description would be as follows. If an atom were the size of a baseball field, then a fly at the center of the field is the nucleus, and electrons are 2 tiny gnats buzzing around the stadium. In truth, the atom is mostly just empty space. All atoms of a particular element have a unique number of protons. For example, an atom with 6 protons will always be identified as a carbon atom, and an atom with 8 protons will always be called oxygen. For this reason, chemists classify atoms by their proton, or really I should say atomic number. An atom's mass number is the sum of the protons and neutrons in the nucleus. The mass of a proton and neutron are almost the same and expressed in a unit of measure called daltons. An atom's atomic mass is approximately equal to its mass number. The slight difference results from electrons, which are about 1/2000th the size of protons and neutrons. In order for an atom to be stable, the positive protons must match the negative electrons in number. As we'll see more clearly in the next few slides, elements bond through each other through the interaction of their electrons. This in turn makes the chemical identity of a substance dependent on its electrons and to an extent protons, but not the neutrons. In truth, because a neutron has no charge, it can be more prevalent in the nucleus without ever changing the number of electrons. These type of atoms are called isotopes. As a general rule of thumb, as long as the neutron to proton ratio is between 1 and 1.5, an atom will be stable. However, if the ratio hits or exceeds this range, there's a high probability the isotope will become radioactive. This means that it can spontaneously decay, releasing particles and energy. As it turns out, even though isotopes may behave similarly in bonding, they are easily identified by radioactive tracers. This makes them very valuable in experiments. One prime example of this is using carbon-14, normally carbon-12, to find out what route carbon takes during photosynthesis in plants. Isotopes have also proven useful in helping us fight against Alzheimer's, a neurological disease caused by an excess of beta amyloid in our brain synapses. Recently, scientists have discovered a protein called PIB which bonds to beta amyloid. Thus, by using isotopes, we've been able to find out where the disease is concentrated. A few slides ago, we took a very brief look into a sort of planet in orbit diagram of the atom. More formally, it's known as Bohr's model. Each concentric ring in the model represents a different energy level or electron shell. These energy levels can be thought of as physical distances away from the nucleus. The farther away an electron is from the nucleus, the higher its energy level. Now, as we look into the diagram peeking in from the left, we find that each energy level is composed of its own sublevels. For this video, we're concerned with S, P, and D. As the energy level increases, sublevels are added. The K shell has only one sublevel, S. The next one has an S and P, and the one after has an S, P, and D sublevel. As new sublevels are added on, the number of orbitals each one can carry increments by 2. For example, S carries 1 orbital, P carries 3 orbitals, and so on. But what exactly is an orbital? Taking a deeper look, we find that each orbital may contain a maximum of 2 electrons. As shown by the diagram in the upper left, the electrons spin opposite to each other as a result of their repulsion. If one is moving up, then the other must move down. This property is known as the Pauli's exclusion principle, and it also explains why an orbital can carry only 2 electrons. There are only 2 ways electrons can have opposite spins. Now, if you're super clever, you may have noticed that the total number of orbitals that an energy level can carry actually follows the form of a quadratic because it grows linearly. Using the function f of x equals x squared, where x refers to the energy level, we find the total number of orbitals per energy level. For example, the third energy level can carry 3 squared or 9 orbitals. Going even further, we find that because each orbital can carry 2 electrons, by multiplying x squared by 2, we may also find the maximum number of electrons an energy level can carry. Now, before I move on, I just want to clarify that orbitals are not some sort of smaller orbit inside of sublevels. They're more like geometric shapes, which electrons are likely to be found in. But what exactly does that even mean? To understand that, we need to look at the electron cloud. As shown in the left, the s orbital has the shape of a sphere. So here in the right, we have an 1s orbital, and just fading in, we have the 2s orbital. So far so good, right? Well, from here it starts to get a little crazy, because p orbitals have a more dumbbell shape, and since there are 3 of them, they want to be as far away from each other as possible, so they spread out across the x, y, and z axis, making them all perpendicular to each other. Going even further, you can imagine that the 3s orbital is another sphere that almost surrounds the other lower energy orbitals. Just keep these orbitals and their respective shapes in the back of your mind. We'll look at them a little bit later. Here we're going to take a very brief look into the periodic table of elements. The table is divided as such. The number of protons increments by 1 from left to right. Vertical columns are called groups. Horizontal rows are called periods. Each period represents a different energy level. Due to the organization of the table, a few special groups may be named. Nonmetals, alkali metals, alkaline metals, metalloids, transitional metals, post-transitional metals, halogens, and finally noble gases. Now, before we move on, I'd like to talk about electron configurations. Because each atom has a unique number of protons and therefore electrons, we can write the different atoms through their electron configuration. For example, hydrogen is written as 1s1. The one in the beginning represents its energy level, The S represents the orbital in that energy level, and finally, the last one shows that there's one electron in the S sublevel's single orbital. Looking at lithium, it is written as 1s2, 2s1. This means it filled up the first energy level K, and in the M shell, it filled up one electron of the 2s sublevel's orbital. As you can see, writing the configurations gets slightly confusing after the third energy level, so you can actually simplify this by writing the closest noble gas in brackets, then adding on electrons which are not already implied. This is called noble gas notation. Now, I'd also like to mention that this pattern we observed does not follow through beyond the third period. Lots of molecular forces, such as shielding, start to come into play. This results in properties such as the 4s orbital being in a lower energy level than the 3d. If you're interested in this kind of stuff, I suggest you follow the links in the description. Great, now that we've taken a look at the periodic table, it's time we examine chemical bonds. For this video, we'll mainly focus on covalent and ionic bonds. Covalent bonds are formed through the sharing of electrons. Two or more atoms held together by covalent bonds form a molecule. There are four ways to represent molecules: the molecular formula, an electron distribution diagram, the structural formula, and finally the space-filling model. We'll ignore the last one just because of how rarely it's actually used. Because each energy level can hold only a certain number of electrons, each atom has a bonding capacity or limit to how far they may branch outward before they fill up their electron shell and become stable. We call this the atom's valence. If an atom such as neon has a valence of 0, then it is chemically inert, meaning it doesn't react to pretty much anything. On the other hand, if an atom is close to filling up its valence and finally being stable, it will react with other elements to do so. As a general rule, a chemical reaction takes place if, and only if, the products are more stable than the initial reactants. Here we see two hydrogen atoms sharing their single electrons. By doing so, the hydrogens will alternatingly fill their individual electron shell. This sort of pass-and-go form of stability is favorable compared to not filling up the shell at all. For this reason, in nature, hydrogen bonds together to form H2. If you look carefully, you may notice the structural formula has a single dash. This indicates that a single electron is being shared by each hydrogen. Here we have oxygen, which shares two electrons. This is known as a double bond. Now, water is a very special molecule because it introduces us to the idea of polarity. Atoms in a molecule are in a constant tug-of-war for shared electrons. An atom's attraction for electrons is measured through electronegativity. Molecules with an equal distribution of electrons are said to be nonpolar, while unequal distributions are termed polar. In the previous example, the molecules were composed of the same elements, so they exerted an equal pull for their shared electrons. However, this isn't the case with oxygen and hydrogen. Water is a polar molecule because oxygen is very electronegative. This makes electrons, on average, hang around oxygen more than hydrogen, ultimately resulting in a slight negative charge. Now, you may be wondering why I decided to circle the structural formula in red. Well, the reason is because, unlike the other molecules we've been examining, water is a bent molecule. But why is that the case? To understand that question, we should take a look at methane and the electron configuration of its central carbon. Here we see a standard diagram of the orbitals, x-axis, and the respective energy levels, y-axis. Notice how the 1s is very far away from the 2s, while the difference between 2s and 2p is relatively small. This difference in energy is the main reason why chemists divide sublevels into electron shells. In order to draw up this electron configuration properly, we need to use two rules. The Aufbau rule says that electrons are added from lowest energy level up, or in other words, the negative electrons are stacked as close to the positively charged nucleus as possible. Well, that's great, but what about the single electrons in the 2p sublevel? This results from the hundredths rule, which states that electrons want to be as far away from each other as possible, so they fill up all the orbitals in their respective sublevel before grouping together. Remember, electrons are both negatively charged, so they repel each other. Now, based on this configuration, we would expect that carbon could only form two bonds, but that contradicts what we observe in methane and various other molecules, where carbon can branch out in four directions. To explain this, chemists have thought up the idea of SP3 hybrid orbitals. Here, an s orbital and three p orbitals sort of merge together to form four sp3 hybrids. Further explanation is beyond the scope of this video, so just think of hybridization as the universe's way of getting carbon to fill up the second electron shell. Well, what does this actually imply in terms of orbital shape? Well, we know that p orbitals are dumbbell shaped and the s orbital has a spherical shape. So when they merge together, they form a shape with a small back lobe and large front lobe. Now, in an actual molecule, all four of these sp3 hybrid orbitals need to scrunch together without overlapping. Remember, the electrons were attracted to the nucleus but repel each other. But how exactly is this accomplished? Well, as it turns out, this can actually be visualized quite easily by using balloons. Here, and in the actual carbon molecule, the balloons form a regular tetrahedron. Now, with all these lobes, carbon can form 4 bonds with hydrogen and form methane. Here, I wanted to make the shape of the tetrahedron easier to visualize. Just as a reminder, the actual shape of the molecule isn't a tetrahedron, but connecting each of the sp3 hybrid orbitals forms a resemblance to this shape. I also want to highlight this triangle in red, because the angle formed is exactly 109 degrees and 28 minutes, which, as you may expect, is the actual bond angle in methane. For those of you who are interested, I challenge you to prove this to yourselves. Just as a small warning, you will need to have basic knowledge of trig to do this formally, but using SSS, you can at least reason that the angle must be fixed. Good luck. Here we see oxygen, pink, and 2 hydrogen atoms, white. In preparing to bond with the hydrogen, the oxygen undergoes sp3 hybridization, forming a tetrahedron. With the oxygen ready, the hydrogen swiftly swoop in, forming a water molecule. Now, before we finally move on, I just want to add that this bond formed between oxygen and hydrogen is actually known as a sigma bond. So, we explored the bend shape of water molecules due to the tetrahedron shape of oxygen. But another question you may have is why exactly oxygen is very electronegative? Well, a very intuitive answer may actually be found by examining the periodic table. In this diagram, I replaced all element names with a Bohr model representation of them. The element circled in red is fluorine, which is the most electronegative element, with oxygen and nitrogen being a few close runner-ups. The reason fluorine is so electronegative is the result of an optimization between the mass of the nucleus and distance of electrons. Fluorine is 1 electron away from filling its octet, so it's very reactive. But what separates fluorine from other metals such as chlorine is the distance of its electrons. Being in the second energy level, its electrons are super close to the nucleus. Compared to chlorine, whose electrons are in the third energy level, the electromagnetic force between its protons and the far-away electrons is simply not as strong. But what about hydrogen? Aren't its electrons super close to the nucleus? Well, the difference is that fluorine's nucleus has 9 times as many protons. With such a difference, you can imagine that the electromagnetic force between the protons and electrons easily makes up for this difference in distances. Now, let's take a look at ionic bonds and table salt. Sodium has 1 electron in the third energy level, so it turns out it would actually be more stable just letting go of it. Chlorine, on the other hand, is only 1 electron away from filling up its octet and again becoming stable. So as it turns out, when sodium and chlorine meet in nature, sodium donates an electron to chlorine. This results in sodium having a positive charge and chlorine having a negative one. Atoms with an overall positive charge are called cations, while atoms with an overall negative charge are called anions. Since positives and negatives attract each other to balance out, the sodium and chlorine combine together in what's called an ionic bond. And from here, you can imagine that multiple sodium and chlorine may kind of gridlock together to form a salt crystal. Now, before I move on, I would like to stress that there's no such thing as a molecule of salt, because sodium and chlorine are not covalently bonded together. It turns out this idea of positives and negatives attracting also extends to water in its liquid form. Recall that oxygen is highly electronegative, so electrons on average spend more time next to it compared to hydrogen. This results in a slight negative charge, which exists most of the time, but not always. I know, kind of weird, right? Well, the result of this is that bonds may spontaneously form and break between the hydrogen of one water molecule and the oxygen of another. We call these very weak interactions hydrogen bonds. Water has many interesting properties that result from hydrogen bonding. As you may imagine, hydrogen bonds make water rather difficult to break, so it has a high surface tension. Many insects, such as katydids, use this property to skip across water. Water also has a high adhesion, meaning it clings to other substances very well. Plants use this property to transport water up their veins. Water is also special because it's one of the very few liquids which is denser as a liquid than a solid. We'll see why in the next slide. Evaporative cooling refers to how water is a very important component of thermoregulation. When our bodies are hot, we tend to sweat. When we do this, the hottest water evaporates away, leaving colder water, which ultimately cools us down. Finally, arguably the most important property of water is its ability as acting as a solvent. A solution is a mixture of two or more substances. The dissolving agent is called the solvent, and what is actually dissolved is called the solute. Water is quite special because it has the ability to break down compounds and catalyze reactions, as we'll see when exploring acids and bases. Here we're taking a deeper look into water at the molecular level. As you can see from the diagram, water in its frozen form tends to form bonds at arm's length across. This results in less stuff being in the same amount of area, which is really just the definition of having a lower density. Because of this density difference, ice floats on top of this glass. Finally, the last topic of today's video is the pH, our potential hydrogen scale. A few definitions to note. Acids donate H+, are protons to a solution. Bases pick up protons from a solution. Buffers act as acids or bases depending on the concentration. Finally, human blood maintains a strict pH of 7.4. Here we take the example of hydrochloric acid, which, as you may expect, donates a hydrogen ion to the solution. But how exactly does this happen? Well, the first step happens when hydrogen meets chlorine in nature. Hydrogen, having one proton, also has one electron, so it would be stable either donating away or filling up its doublet. In the case of chlorine, it donates it away, giving hydrogen a positive charge and chlorine a negative one. Because they have opposite charges, the two are ionically bonded together. Now what happens when this compound is placed in water? Well, we can actually imagine that the water molecules almost surround the compound. The oxygen, being negatively charged most of the time, swoop in from all directions and eventually force the hydrogen to be broken apart. Since the extra proton is added to the solution, this is a very potent acid. Next up, we have sodium hydroxide. Much like in salt, sodium has one electron in its outermost cell, so it would be more stable giving it up to another compound that needs it, such as hydroxide. Remember, oxygen has a valence of 2, and hydroxide only has one electron being shared. With this extra electron, we have two opposite charges, which are ionically bonded together. Now, much like with hydrochloric acid, sodium hydroxide is forced to dissociate into hydroxide and sodium. When this OH group comes into contact with a hydrogen ion, it'll readily bond with it to become a very stable molecule H2O, aka water. Because this reduced the hydrogen concentration of the compound, it is classified as a base. Thanks for watching. That's all I have for this video. See you next time.